Hi, welcome everyone to the Monday SITP colloquium. Today we are very happy to have Professor Ofer Aharony from the Weizmann Institute, and he's going to tell us about some recent work on constructing an explicit theory of quantum gravity. Over to you, Ofer.
Okay, thank you very much. Thanks for the invitation to give this talk. I mean, hopefully only this once remotely, and next time I hope to be there in person. Okay, so since this is a colloquium talk, and I hope that there are at least some people who are not experts in the field, I will start with a rather general review of the problem of quantum gravity, and also a review of the Cf2 Correspondence, which is our main current solution to this problem, with some examples. So there are many experts in the audience, so all the experts are welcome to decouple for half an hour and then come back if they want to. And then in the second part of the talk, I'll present a derivation of the Cf2 correspondence for a specific case, one of these examples, the case of vector models. And this last part is based on a couple of papers that I wrote in collaboration with our excellent postdoc and student, Shai and Erez Urbach. So let me start with a general review. So maybe it's not necessary in this audience, but still, just to be complete. So the problem of quantum gravity, of course, comes from the main revolutions that happened in physics around 100 years ago, general relativity and quantum mechanics. And even 100 years later, we still don't know, at least in 4 space-time dimensions, how to write down theories that are consistent with the principles of both of these revolutions. General relativity, to remind you, is a classical theory describing the gravitational interactions via the metric in space-time. So the metric in space-time responds to the matter field through Einstein's equations. And of course, this is a very successful classical theory, agreeing with all measured gravitational interactions from the lab scale through stars and black holes and all the way to cosmology. Quantum mechanics, of course, needs no introduction. It's the basis of all modern physics. And in this talk, I'll focus in its implementation in relativistic systems, namely in quantum field theory. So one standard way to formulate quantum field theory is to take the basic objects to be fields, phi of x, generalizing the electromagnetic field. But in the quantum theory, these are operators, and one can view them as describing local degrees of freedom at every point in space-time. So generally, x in my talk will denote a point in space-time. And one way to describe a quantum field theory is by giving the set of fields and then the local interactions between them. So the action or the Hamiltonian will generally include interaction terms like this, where we have some product of fields at the same point multiplied by some coupling constant Gj. When the coupling constants go to 0, we have free fields. And for small couplings, we can use a perturbation theory. But an important issue is that quantum field theory is well defined. Also, when the coupling constants become large, for instance, we can use the path integral formalism to define the theory through the path integral, regularizing it somehow by lattice or some other regularization. And those regularizations do make sense for all values of the coupling. However, of course, the theory is harder to analyze at strong coupling. Now, the typical observables in quantum field theory are correlation functions of local operators. So for instance, you could take phi to the 4th x as an example of a local operators. And then typically what we would compute in quantum field theory would be some correlation function of these local operators. And from those, we could obtain the scattering amplitudes and all the other measurable objects in the theory. Now, it's important that not any interaction gives us a consistent quantum field theory at all scales. The only ones that do are the normalizable quantum field theories, where we have just a finite number of couplings that are important at short distances, and then the values of those couplings determine the theory at all scales. And of course, the specific renormalizable quantum field theory, the standard model, with its specific fields and 26 parameters, describes nature extremely well, as far as we know so far. Now, it's natural to expect that gravity should also be described quantum mechanically, but unfortunately, this is very hard to check experimentally because gravity is typically measured at long scales, while quantum effects usually become important at short scales. And just by dimensional analysis, we can estimate the scale where quantum gravity effects are expected to become important. And the scale that you get by forming a combination with units of length from h bar, g Newton, and c is the Planck scale, 10 to the minus 33 centimeters, which is, of course, orders of magnitude smaller than any scale that we can hope to experimentally access. So it's therefore very difficult to study quantum gravity experimentally. Now, one may hope that this would be a situation where we could actually write down many different theories and then not be able to distinguish between them experimentally. So we'd be in a tough situation from that point of view. But in fact, the situation is the opposite. It turns out to be very difficult to construct any consistent quantum theory of gravity, even without having any experimental constraints on it. The most naive attempt to construct such a theory would be just to try to build a quantum field theory using as the basic field variables the metric g mu nu x, and then using the action of general relativity coupled to matter fields. But if we try to do this and 3 space-time dimensions or higher, we find that this theory is non-renormalizable. So we must have an infinite number of parameters to specify the theory, and we don't get any predictive theory. And presumably, quantum field theory just is not the correct framework to describe quantum gravity. Of course, we do expect in quantum gravity that space-time itself should fluctuate, so we don't expect to have any well-defined operators sitting at well-defined points in space-time, and therefore quantum field theory is presumably not relevant. And indeed, the well-defined observables and theories of quantum gravity are not correlation functions of local operators, but rather scattering amplitudes. So the naive definition that one would try to give to a quantum gravity theory by a path integral over metrics, presumably sum over topologies and so on, while that does make sense in low dimensions, as some people in the audience have analyzed extensively, it does not make sense in 3 space-time dimensions or higher. So we need something completely different. And the best attempt that we have so far at this something completely different is string theory, where we replace local fields by strings of some typical size Ls, which is related to the tension of the strings, and therefore that sets the size of typical excitations of the string. At long scales compared to the string scales, excitations of the string look like particles, and many different, well, a string can generally have many different excitations that will look like different particles. And the nice thing about string theory is that quantizing strings automatically gives a theory of quantum gravity, because one of the excitations of the string is always a graviton, namely a massless spin 2 particle. Now, the simplest solutions of string theory live in 10 space-time dimensions, but we can compactify 6 of those to get theories, say, with 4 large space-time dimensions, and therefore string theory does give us quantum gravity theory also in 4 dimensions. Unfortunately, there are many different solutions of string theory, and we do not yet know if any of them describe our universe. So in quantum string theory, we can compute quantum corrections to graviton scattering by following the rules of perturbative string theory, but unfortunately, string theory is only understood so far in a perturbation theory in the coupling constant G string between strings, and this perturbation expansion does not converge. So far, all that we have in string theory is a perturbative expansion, and we do not yet have any non-perturbative definition of string theory analogous to the path integral or some regularization of it for a quantum field theory, which would make it well-defined for finite values of the coupling constants G. So string theory is not yet a complete theory of quantum gravity, and so far, indeed, in flat space, we don't have any complete theory of quantum gravity. So this was a very quick review of quantum gravity, but let me still stop and see if there are any questions at this stage. Feel free also to interrupt me with questions at any time during the talk, of course. I mean, I'll try to stop after every part for questions, but do feel free to interrupt me at any point. Okay. So in the next part of the talk, I'll review the Cf2 correspondence. So even though in flat Minkowski space, we do not yet know how to formulate a quantum theory of gravity, the Cf2 correspondence found almost 25 years ago does tell us how we can formulate such a theory in a different spacetime, namely anti-de Sitter space. So anti-de Sitter space is the maximally symmetric spacetime that has a constant negative curvature, just like the maximally symmetric spacetime with 0 curvature is Minkowski space, and with positive curvature, it's de Sitter space. And the Euclidean version, which would be maximally symmetric with negative curvature, is what's called hyperbolic space. This space is a solution to Einstein's equation with a negative cosmological constant. And one way to view the space, as in this figure, is to imagine that one direction is the time direction, and then the spatial slices look like the hyperbolic plane. Here I drew it with 2 space dimensions, but it's a similar construction also in higher dimensions. So at each time slice, we have this hyperbolic space where the metric is such that the length of each of the fish in this Escher drawing has the same length, so that the length of each of these fish is the same, and in particular, the length to the boundary, even though it's drawn here at finite distance, the length to the boundary is actually infinite, because there's an infinite number of fish that you have to go through to get all the way to the boundary. So naively, if the boundary is infinitely far away, you may think that we don't care about it, but because of the way that the metric of anti-de Sitter space is constructed, light rays can actually bounce off the boundary and back at a finite time, and therefore the boundary does causally influence the interior of the space. Now, it's very important in anti-de Sitter space that because the distance to the boundary is infinite, and also the distance between points in the boundary also diverge, then the metric at the boundary itself does not fluctuate, while the metric in the interior does fluctuate. So in a theory of quantum gravity in anti-de Sitter space, the metric does fluctuate in the interior of the space, but the metric at the boundary does not fluctuate. You may wonder, otherwise, what it even means to say that we have a quantum gravity theory on a anti-de Sitter space, because in quantum gravity, of course, space-time itself fluctuates, so we shouldn't be able to say which space the theory lives on. But what we really mean by saying that is that we have a quantum gravity theory on a space which is asymptotically anti-de Sitter space, so it has the same boundary, where the metric does not fluctuate. While in the interior, then naively, we do need to sum over all the metric fluctuations. So I'll denote by L the radius of curvature of this anti-de Sitter space, which is related to the cosmological constant when we view it as a solution of Einstein gravity. I'll denote by Z what's called the radial coordinate of anti-de Sitter space, which goes to 0 at the boundary and then grows towards the interior. And I'll denote by X mu the coordinates of anti-de Sitter space that are parallel to the boundary. Now, since the metric at the boundary of anti-de Sitter space does not fluctuate, it does make sense to insert local operators at the boundary of the space, because points on the boundary are well defined. So we can put in sources at the boundary and see how the bulk theory responds to them. And in particular, the list of observables for a quantum gravity theory on d+1 dimensional anti-de Sitter space includes insertions of local operators at points on this d-dimensional boundary. And therefore, the list of observables looks very similar to the list of observables of a quantum field theory in d space-time dimensions. Namely, we can just insert local operators that sit at the boundary but are labeled by these d-dimensional positions and by putting in a source for some specific field. And this observation motivates the Cf2 correspondence, which is the statement that not only is the list of observables the same in these two types of theory, but in fact there is a precise equivalence between these theories, namely a quantum gravity theory on an asymptotically anti-de Sitter space in d+1 dimensions is equivalent to a d-dimensional quantum field theory. And indeed, if we had some quantum gravity theory of this type, then these observables would be well defined, and one can argue that they would obey all the axioms of a quantum field theory, so that they would define, if you want, a d-dimensional quantum field theory. And in fact, it's not just any quantum field theory, but you can show that because of the isometries of anti-de Sitter space, so anti-de Sitter space turns out to have this in d+1 dimensions, it has an SOD2 isometry group, and the way that that acts on these d-dimensional coordinates on the boundary of the space is as conformal transformations, which include the Poincare symmetries that we have in any relativistic quantum field theory, but they also include scale invariance and special conformal transformations. So the theories that are believed to be dual to quantum gravity on ADS space are in fact conformal field theories. Now, this would be the statement if we had a definition of such a quantum gravity theory, but of course, in fact, we do not know how to define quantum gravity theories, not in anti-de Sitter space or in any other space a priori. So this correspondence should in fact be viewed as giving us a definition of what we mean by the left-hand side, namely the quantum gravity theory on anti-de Sitter space, and we can define it as being equivalent to this d-dimensional quantum field theory. So the challenge then is to understand precisely which conformal field theories are actually dual to quantum gravity theories on anti-de Sitter space, and precisely how this mapping works, namely how do we show that indeed our quantum field theory does describe what we would like to call a quantum gravity in anti-de Sitter space. In particular, it should have an appropriate classical limit where it describes classical gravity on anti-de Sitter space, and then include in it all the quantum effects in the natural, or at least in a self-consistent way. Now, of course, an equivalence of this type between two very different theories at first sight sounds completely preposterous. We match here theories that not only have different variables, different fields in them, but even live in a different number of space-time dimensions. But we know by now of many examples in quantum field theories of dualities of this type, where we have two different descriptions of the same system that use two very different sets of variables. Some famous examples are particle vortex duality, Kramers-Bonnier duality, S duality, and so on. So by now we've gotten used to the idea that we can start a twee coupling in some quantum field theory with some set of fields, and then as the coupling increases, the quantum effects become large, the theory rearranges itself, and eventually when we go to strong coupling, the same theory can become equivalent to some completely different field theory at weak coupling. So in quantum field theory, we have by now many examples of that behavior. Well, certainly in 1+1 dimensions, but also by now in 2+1 and in 3+1 dimensions. And the claim is that something similar is happening here, but in this case, where one side is not a standard quantum field theory, but a theory of quantum gravity, and it also lives on a different spacetime. So this is a more extreme example of a duality of this type, but it is still just some rearrangement of the degrees of freedom that happens when we go to strong coupling. However, there is an important difference between the Cf2 correspondence and field theory dualities. In field theory dualities, usually the expansion in small h bar, so the semi-classical expansion of one theory in a duality pair maps to the large h bar expansion in its dual description. So we have a mapping between the weak coupling regime of one theory and the strong coupling regime of the other theory. However, in the Cf2 correspondence, the situation is more interesting. In particular, we could have two independent parameters such that these two expansions, the weak coupling expansion of one theory and the strong coupling expansion of the other theory, are actually not the same. So let me illustrate this in the prototypical example of the Cf2 correspondence, the first one that was found 24 years ago, namely the equivalence between type 2b string theory on ADS5 cross S5. So this is some specific example of a string theory that we know how to define perturbatively, and which lives on a space which is the product of the 5-dimensional anti-de Sitter space times a 5 sphere. So the left-hand side in this case is a theory that we do understand perturbatively as a string theory, but a priori we don't have any non-perturbative way to formulate it. And the claim is that this is equivalent to a specific non-abelian gauge theory in 4 dimensions, which in this case is the famous n equals 4 supersymmetric SUN Young-Mills theory, which is some specific Young-Mills theory coupled to 6 scalar fields and 4 fermion fields and adjunct representations. The details of the theory are not so important. What is important for the purposes of what I want to say is that in this quantum field theory, it turns out that it has just 2 parameters. One parameter in this case is n, which is the rank of the gauge group, SUN. So all the fields in this theory are n by n matrices. And the other parameter is the gauge coupling constant, Young-Mills. It turns out that all the other coupling constants in this theory between the scalars and the fermions are just related to Young-Mills by the symmetry. So we don't have any other independent coupling constants. Usually in Young-Mills theory, the coupling constant is not really a parameter because it runs with a renormalization group and it gets transmuted into a scale. But in this case, the beta function of the theory vanishes. So we do actually have a field theory and indeed a conformal field theory for every value of this parameter at Young-Mills. And therefore the theory is labeled by one discrete parameter n and one continuous parameter Young-Mills. And the quantum corrections are, of course, controlled by this coupling constant as usual in quantum field theory, or in fact, in this specific theory, if we look at large values of n at least, then quantum corrections are typically controlled by this, what's called the 't Hooft coupling lambda, which is this combination of Young-Mills squared and n. So those are the parameters on the field theory side. On the string theory side, we similarly have also 2 parameters. Obviously, otherwise we couldn't claim they're equivalent. In string theory, we can take the 2-dimensionless parameters. One of them, we can take it to be the Newton's constant of the gravity that we get from this string theory, measured in units of the anti-de Sitter radius L. So that's G Newton over L to the 8th, and that's what controls the strength of the gravitational interactions, and in particular, also the strength of the quantum corrections, like graviton loops and any other quantum corrections that we would have in this space. So that's one parameter. And the other parameter is the size of the anti-de Sitter curvature compared to the typical size of a string. So that controls the locality of the theory. We could have one limit where ADS spaces has a radius of curvature much bigger than the string scale, and then the theory is approximately local because the typical size of strings is much smaller than the radius of curvature of the whole space. But this ratio could also be of order 1, and then the theory is highly non-local because the radius of curvature is at the same scale as the typical scale of our states. Now, the way that the mapping works is that this parameter Gn over L8 that governs the quantum corrections on the anti-de Sitter side maps to 1 over n squared on the field theory side, while the parameter that governs the quantum corrections on the field theory side, this coupling Young-Mills squared n, maps to this non-locality parameter on the gravity side. So if we look at this 2-dimensional space of parameters of this theory, one is this discrete parameter n, but I'm drawing it here as continuous, and then we have this other parameter which really is continuous, lambda. So from the quantum field theory point of view, on this right-hand side, the quantum field theory is strongly coupled for any value of n, while on this left-hand side, the quantum field theory is weakly coupled for any value of n. The gravity theory is weakly coupled whenever we have large n. So on the top of this diagram, well, it's strongly coupled when n is small at the bottom of this diagram. But when we go from right to left, what happens in the gravity theory is that on the right-hand side, gravity is approximately local. That corresponds to the regime where the quantum field theory is strongly coupled. But on the left-hand side, gravity is highly non-local in the sense that the typical size of strings is of the same order as the curvature scale and all the other scales in this gravity on anti-de Sitter space. So the theory is highly non-local. But the interesting thing is that the quantum the expansions in H bar, if you want, on the two sides do not map to each other. The expansion in H bar in the field theory corresponds to this horizontal axis, while the expansion in H bar in the gravity theory is this vertical axis. And in particular, we do have a limit where both sides are weakly coupled and semi-classical, which is this limit of large n and lambda goes to 0. Now, this correspondence has not been proven yet, but we have many tests of it by now. Of course, so the extended supersymmetry helps a lot in this. What we would like to have is really a derivation of this correspondence. And again, since the left-hand side is only defined in string perturbation theory, what a derivation in this case would mean would be showing that we can get from the n equals 4 super-Yang-Mills theory, we can rederive in the large unlimit the whole perturbative expansion of type 2b string theory on this space. But unfortunately, so far, we have not been able to show this. And in fact, even in the limit where it should be easy to show it, so we have this limit n goes to infinity, lambda goes to 0, where both sides are classical, and then we're just supposed to show that we have an equivalence between two classical theories. But even in this limit, where it should be much easier, we still have not been able to completely derive the correspondence, although there is slow progress being made on this front. And the reason that it's difficult is that the two classical theories here are rather complicated classical theory. On the string theory side, we have just classical strings, but they live on a highly curved ADS space, while on the field theory side, we have just a free SUN theory, but it is still a gauge theory where we have a Gauss law constraint that complicates the spectrum. So because of these complications, let me look for a simpler example where we should perhaps have an easier time deriving the correspondence, and we'll see that that is indeed the case. So in the rest of this talk, I'll discuss this second example of the Cf2 correspondence that was introduced by Klebanov and Polyakov almost 20 years ago. In this case, on the field theory side, we really take the simplest possible theory, just n free massless complex scalar fields phi I of x, and the action is just the action of these n free massless scalar fields. It can be in any number of dimensions bigger or equal to 3. So we just have these n free scalar fields. Of course, if these fields would really be completely free and decoupled and not talk to each other, then this theory would not have a nice large unlimit. But in order to have a nice large unlimit, we need to project this theory just to singlets of the UN global symmetry. And then the resulting theory, which is often called the vector model, does have a nice large unlimit. This projection to singlets, I mean, it's, well, in flat space, we can really just do it by projecting out the Hilbert space and just looking at states that are invariant under UN and operators that are invariant under UN. Doing it on more complicated manifolds is more complicated, but here in this talk, from here on, I'll just focus on the theory in flat space, where we can just do this projection in a straightforward manner. So the field theory that I'll discuss from now on is this UN singlet sector of the theory of n free massless fields. The local operators in this theory are the local operators that are UN invariant that we can construct from these scalar fields. So the simplest ones are just taking phi I dagger times phi I and summing over n to get something that's I going from 1 to n to get something that's UN invariant. And then we can sprinkle various derivatives acting on these fields. Of course, that's still UN invariant. And it turns out that we can construct spin J operators by taking these derivatives in an appropriate way. And in fact, the full list of local operators in this, of UN invariant local operators in this field theory, is just these spin J operators OJ, their derivatives, and the products of these states and their derivatives. So that turns out to be the full list of local operators in this theory. It turns out that all these currents OJ for any spin J are conserved. For J equals 1, this is just the generator of the UN global symmetry. For J equals 2, this is just the energy momentum tensor. But also for higher spin, these are still conserved currents. So this free theory, maybe not surprisingly, has a huge symmetry group with conserved currents of all spins. Now, the rules of the Cf2 correspondence tell us that whenever we have conserved spin J, what are called single trace operators of this type in the conformal field theory, then those should map to having massless spin J fields living on d+1 dimensional anti-de Sitter space. So we should have on the gravity side a theory that has these massless high spin fields for all spins. So that includes the graviton, but also high spin states. So theories of this type are called high spin gravity theories. They're, if you like, natural generalizations of gravity, where we don't just have the spin 2 graviton, but also its higher spin generalizations. It's of course rather natural to look for theories of this type, since we do have a spin 2 graviton, but it turns out that even classically one cannot write down any consistent theories of this type in Minkowski space, which is why these theories are not very common. However, Vasiliev showed already many years ago that it is possible to write down classical theories of this type in anti-de Sitter space. And these theories, of course, have a huge gauge symmetry. So just like the spin 2 massless field is associated with the diffeomorphism symmetry, each of these massless spin J fields is associated with a huge symmetry group of its own. So these theories have some huge gauge symmetry. And these theories, again, they're known as just classical equations of motion for these high-spin fields in anti-de Sitter space. And when sees, well, so far it seems that this theory is just unique, namely given this huge symmetry group, there's just a unique theory that can be written down, and that theory is non-local at the scale L, and it has just a single coupling constant that appears in the equation of motion, which we can identify as Newton's coupling, since it also governs the coupling of the gravitons. So in this case, on the gravity side, at least in the classical limit, we see that we have a theory with a single coupling constant. And so
a quick question.
Yes.
Is there
Sure.
some intuition for why ADS is better than Minkowski for these higher spin theories?
Yeah, well, the only intuition I have is that the theory sort of comes together with a non-locality scale, and in ADS we have this natural scale L that can fit the bill of giving us this non-locality scale, so that it sort of has a natural built-in scale. I mean, similarly in de Sitter space, you also have a non-local, also have a typical curvature scale, and then again, you can't construct these high-spin gravity theories on de Sitter space. But presumably, if you would try to do it in flat space, then because there is no typical scale, then the theory would just be completely non-local at all scales, and then it's just, I don't know. It's very hard to imagine such a theory whose non-locality scale is infinity. I mean, so it's not something that we would even know how to imagine. Well, in this case, at least, it has a finite non-locality scale.
The theory is local at scales larger than L. Is that the idea?
Well, I mean, yes. Well, to the extent that scales larger than L makes sense. I mean, but yeah, in anti-de Sitter space, I mean, everything sort of is typically at the scale L. I mean, so there's just one scale. The theory is not local at that scale. So yeah.
Okay.
So, but I mean, that's not that's just intuition. I mean, I'm certainly not an expert on high-spin gravity. I think at the technical level, I mean, there are no-go theorems for that. I mean, of course, I mean, I'm sure you know the usual no-go theorems just for various forms of high-spin interactions in flat space. So, but I don't have any good intuition beyond that, I'm afraid.
Okay, thanks. Yeah.
So in any case, on the field theory side, in the field theory that we constructed, the only parameter was this discrete parameter n. On the gravity side, the only parameter here is this g Newton, which we can make dimensionless by measuring it in units of the ADS scale. So it's natural to identify by a duality these two parameters with each other. And indeed, in this case, the gravitational coupling maps to 1/n, such that in the large n limit, both sides are classical, just like in the previous example with lambda equals 0, except that in this example, of course, the field theory is just a free field theory, so it is completely classical for any value of n, but the gravity theory also becomes classical in the large n limit. So again, we have this weird case of a duality where both sides have a semi-classical limit at the same time. Now, in this case, again, calling it a duality is maybe a bit of a strong word, because the quantum gravity side in this case is not very well defined. I mean, not only is it not well defined as a quantum theory, it's beyond perturbation theory, but even the perturbation theory in this case is not well defined. All that we really know about these high-spin gravity theories are their classical equations of motion. We don't even have an action that we could try to use to construct what we would call a quantum theory, a quantum generalization of the high-spin gravity theory. And even classically, there are various problems if you try to do some computations, but still there are classical equations. So you can try to test this correspondence by comparing things in the field theory and the large n limit and trying to match them to the solutions to these classical equations of motion. And so far, all the tests that have been done have been successful. So this does seem like a consistent duality. And our goal in the rest of this talk will be to derive this duality. And again, what that means is to show that the large n limit of this quantum field theory can be written as a high-spin gravity theory on anti-de Sitter space. So since that's all we know about the gravity theory in this case, then that is, I think, the only sensible thing to call a derivation of the duality for this case. So this concludes the review part of the ADS Cf2 correspondence. Are there any questions about this part? Okay, good. So if there are no more questions, then in the rest of this talk, I'll try to derive this correspondence, namely prove that the UN singlet sector of the theory of n-free complex scalar fields can be rewritten as a high-spin gravity theory living on d+1 dimensional anti-de Sitter space. And the method.
Sorry to be late.
No, sure.
With the question, as you of all people know very, very well, that you can consider like large flavor theories that have a little bit more interaction than just the gauge projection, like
right,
3D QED and all that at large NF. Does all hell break loose if you try and consider that case, or?
No, to some extent, I mean, it depends what questions you want to ask, but I mean, generally, the derivation that are presented really, I mean, as will become obvious when I present it, it really only makes sense for vector models. So if you have matrix degrees of freedom, even if the matrices disappear through Chern-Simons couplings and so on, but with a large gauge group, then so far I don't know how to generalize it to that case. So in that sense, all hell does break loose. I mean, whenever you have, say, holonomies of some large abelian groups, then yeah, as far as I'm concerned, all hell does break loose. Yes.
Well, so, but if you did a U1 version,
right? But if it's just a U1 coupled to a large number of fields, then that can be done, and indeed, that I'll describe how to do that. Yes.
Thanks.
Okay, so the general method that we'll use to derive this duality is what's called bilocal holography. That was first, I think, introduced by Das and Zawitsky almost 20 years ago, and the variation of it that we'll follow most closely was introduced in this paper from 2018. Of course, bilocal holography is also extensively used in the SYK model that many of you are familiar with. And the basic observation used in bilocal holography is that any operator in the quantum field theory, which is UN invariant, can just be expressed in terms of these bilocal operators, G, X1, X2, which are defined as the product of phi I dagger at X1 times phi I at X2, where X1 and X2 are just two different points in space. So this is obviously a UN invariant operator by construction. And the claim is that any UN invariant operator can be written as some functional of this bilocal field. In particular, of course, the local operators can arise just by doing a Taylor expansion of this as X2 approaches X1. So doing the Taylor expansion gives all these spin J operators that I described before. But I mean, obviously, this is UN invariant even for separated points. And again, the claim is that these are all the UN invariant operators. So what that means is that one way to formulate what we mean by the UN singlet sector of the theory on the field theory side is that we have this path integral over a field phi I with the standard free field action, and we want to compute various functionals of this bilocal. So this is one way to write all the information in the UN invariant sector of this theory. And our goal will be to see whether we can rewrite this path integral in the field theory as a path integral that will describe some quantum high-spin gravity theory living on anti-de Sitter space. So we'll try to rewrite this as a path integral over some fields in anti-de Sitter space so that they'll be labeled by the coordinates x and also this extra radial coordinate z, with some action for these fields and with some functional of these fields that will be mapped to this functional of these bilocal operators. Of course, we don't really expect such a naive writing to make sense on the quantum gravity side, because as we said, we shouldn't even have local operators in the quantum gravity side in general. But what we will see is that it is actually possible to do such a mapping perturbatively in the gravity side, so perturbatively in the gravitational coupling. But we'll see that if we try to go beyond perturbation theory, then we will need to modify this right-hand side. So that will be our goal, will be to show that we can do this mapping perturbatively, but we'll also see why we cannot do it beyond perturbation theory. So the way that we'll show this equivalence is in 4 easy steps. So in the first step, we'll do a change of variables in the path integral from our original field phi I of x to this bilocal field g x1 x2. The second step will be to take this gx1 x2 and to expand it in eigenfunctions of the conformal group. So the thing that we understand best about the Cf2 correspondence is that we have the same symmetry group on both sides. I'll be discussing Euclidean space from here on. So the Euclidean conformal group is this group SOD plus 1, 1, and that maps to the isometry group of the D plus 1 dimensional anti-de Sitter space. And of course, any function, we can expand it in eigenfunctions of this conformal group. And as we'll see, there are some specific eigenfunctions that are appropriate for the action on these bilocal operators. And so we can just expand this bilocal field in these eigenfunctions. And so these are known eigenfunctions. And in the general expansion, we'll have some coefficients. We'll see that these eigenfunctions are labeled by some parameters delta j and y. So we'll have some list of coefficients, c delta j of y, that will be equivalent to specifying this bilocal field. And then in the third step, we'll see that also when we have some spin J fields on anti-de Sitter space, which is our expected field content for this theory, then we can also expand those in eigenfunctions of the same SOD plus 1 group. Of course, the eigenfunctions will be different because these are different objects, but they'll still be labeled exactly by the same labels, delta J and Y. So we can expand them in a similar basis of eigenfunctions, and the coefficients will have a similar form. They will be labeled by the same labels. So that will enable us to construct a mapping between these two sides just by essentially identifying these coefficients here that appear in the expansion of the bilocal field with the coefficients in the expansion of the spin J fields in ADS space. And that will give us an explicit linear change of variables from this bilocal operator to the fields in ADS space that will therefore enable us to derive a correspondence of this type between a path integral in the field theory and a gravitational path integral on ADS space. So in the rest of the talk, I guess the remaining 25 minutes or so, I'll describe each of these steps in turn. So let's start from the first step. So in the first step, we just want to, in the field theory, just change variables in the path integral from our original field phi I to this bilocal field g of x1, x2. Now this step is just in field theory, so it doesn't involve any quantum gravity or anything, but it still turns out to be the most subtle step in this whole mapping, because this change of variables is nonlinear. And the main subtlety is that these bilocal variables, g of x1, x2, are not independent of each other. For instance, if we just take the simplest case where n is just equal to 1, so we just have one field, of course, that's a special case of this mapping. So if n is equal to 1, then this g is just phi dagger x1 times phi of x2. And then if we take the product of two of these bilocals, gx1, x2 times gx3, x4, then that's just the same as phi dagger x1, phi x2, phi dagger x3, phi x4. And of course, that's also the same as gx1, x4 times gx2, x3. So in this case of n equals 1, for any 4 points, we have a relation of this type between a product of these two g's and the product of these two g's. Now, similarly, for higher values of n, the relations are not as simple, but we still have relations if you take a product of n plus 1 g's in the theory with n fields. We find that those obey complicated nonlinear constraints of this type between the g's at any set of points. So again, these g's are highly constrained. In order to analyze these constraints, it's useful to regularize the quantum field theory, since we have here constraints at every point in spacetime, and it's difficult to analyze them with the spacetime is continuous. Then it's useful to regularize the theory by putting our quantum field theory on some lattice with V sites. Once we put our quantum field theory on the lattice, we can view this original field phi I of x as a V by n matrix. That just tells us the value of the ith field at the point x, where x again takes V possible labels. So this phi of x is now a V by n matrix, and g of x1, x2 is now just defined as the matrix product of the matrix phi dagger times the matrix phi. And this is a V by V matrix that's labeled by these 2 points in spacetime. Now in this language, it's obvious that the constraints are that we can we can obtain G as a product of phi dagger phi in this way, if and only if the rank of G is less than or equal to n. So of course, for n equals 1, then the rank of G has to be equal to 1. But in general, we find that the rank of this matrix G has to be less than or equal than n. So now there are two possibilities. One possibility is that we're at large values of n. So if n is bigger or equal than V, then we have no constraint, because of course, a V by V matrix always has a rank less than n in this case. And this will be the case if we first take the large n limit and only then take the continuum limit. So in this case, we don't have any constraint. All the values of G are possible. And what we'll see is that this order of limits will be the order of limits that reproduces for us the semi-classical gravity theory on ADS space. So in this order of limits, we have no constraints on G. We'll be able to easily do this change of variables and obtain just a path integral of gravity fields on ADS space. However, if we're interested in the theory at finite n, and we do want to take the continuum limit of large phi, then these constraints do become very important. Of course, we can still do the change of variables from phi dagger phi to G. I mean, G still does contain all the UN invariant information, but this change of variables now becomes very complicated because it has to take into account this complicated, highly nonlinear constraint on G. So from here on, I won't really say much about this case at finite n beyond just saying that the matrix G is highly constrained in this case, but I'll focus at least for the next few steps on assuming that n is bigger than V, namely we first take the large limit and only then take the continuum limit. And in this case, all values of G can be obtained without any constraints, and we can just map any field configuration phi I to some configuration of these G's. And it's easy to compute the Jacobian for this change of variables from phi I of x to the space of G's. And it turns out to be given just by the determinant of this, again, V by V matrix G raised to the power n minus V. And now that we have this change of variables, we can just rewrite our original field theory path integral as a path integral over this bilocal field with an action which has one term that just comes from taking this free field action and rewriting it in the language of G. So it's just two derivatives acting on this bilocal G evaluated at x equals y. And then we have an extra term coming from this determinant, which we can just write as e to the trace times a log of this matrix G. So this gives us a completely, again, as long as n is bigger or equal than v, then the number of space-time points, then this is a precise equivalence of path integrals, and we don't lose any information by going to this other set of variables. Now, in this new set of variables, of course, it's natural to do a large n expansion if we want. I mean, we see that we have here two terms in the action that are proportional to n, and another term which doesn't involve n, and we can just do a large n expansion around some saddle point of this action and obtain a standard 1/n expansion around that saddle point. The saddle point in this case is not at G equals 0. I remind you that G is this bilocal field. And of course, it does have a non-zero expectation value, which is just the propagator of a free scalar field from x1 to x2. So we expect the expectation value of G to be given by just in d dimensions 1/x1 minus x2 to the power of d minus 2. And indeed, one can show that that is precisely the saddle point of this large n path integral. If you just solve the equation of motion that you get from this action, this is precisely the solution. And then in order to have a nice large n expansion, we just expand G around this large n saddle point. And it's useful to normalize the deviations away from the saddle point with a coefficient of 1/√n. And then once we do that, we just plug that into the action, and we obtain an action for eta, where we have a quadratic term for eta. So this term, I mean, from this G, we would just get a linear term in eta, which cancels with a linear term here, since we're expanding around a solution to the equations of motion. So all the interaction terms in the action actually come from this Jacobian term. So we have a quadratic term in eta with no factors of n, and then we have interaction terms that are proportional to various powers of 1/n. And in this context, we should think of this term v as being some extra counter term. I remind you that v is the number of points in space-time, so we should think of it as some uv cutoff, or as depending on some power of the uv cutoff. So that gives us some counter terms that are necessary for this path integral written in the language of the G's to exactly reproduce our original path integral. So by construction, the path integral that we obtain in these variables eta is completely equivalent to our original path integral. And indeed, we can just do computations in these eta variables. We can do loop computations and so on. And it's easy to check order by order, at least in this 1/n expansion, that any computations that we do with this action for these bilocal variables reproduce precisely the correlation functions of our original free theory. Of course, in the free theory, the 1/n expansion is sort of trivial. It truncates after the first step. So what really happens is that all the loop diagrams exactly cancel with these counter terms, such that eventually all the 1/n corrections vanish, and you can just see that explicitly by doing the large n expansion of this action. So this is the first step. In the first step, again, we just translate our original path integral to a new path integral for these G variables. So are there any questions about this first step?
Let me ask a quick question. We know from SYK model that sometimes life is easier by implementing the change of the Jacobian with an auxiliary field, usually called sigma in that language. Do you get any mileage by doing things that way?
Yeah, so we don't seem to. I mean, so one way to derive this Jacobian indeed is to start from the sigma variable, and then integrating out sigma would exactly give you this Jacobian. But yeah, we haven't been able to. I mean, it doesn't look like you get a simpler theory by doing that. But yeah, I mean, we haven't analyzed anything you can do with it. So I don't really know. But yeah, we haven't been able to get any mileage out of it. That's all that I can say.
Thanks.
Any further questions?
Yeah, maybe just a minor quick question. So the V term, the term proportional to V, is not playing a role in the computing the saddle point G0, right?
That's right, because that's a term of order 1 in the large n expansion. Okay. So indeed, so we view this term as order 1. I mean, it's proportional to some power of the UV cutoff, but it's independent of n. Mm-hmm. So I mean, we have in general, when we compute in this theory, we'd have both. I mean, we have some expansion in powers over UV cutoff whenever we do a computation. We have the 1/n expansion, and you can show that order by order in both of these expansions, you just reproduce the original free theory. So all the dependence on the counter term, of course, eventually cancels, and you just get the free theory.
Okay, thank you.
So Ofer, sorry to slow you down, but
no, since you mentioned, I'm happy to have questions.
It just occurred to me, since you just mentioned a UV cutoff, and you're going to do this all super explicitly, are you going to get a nice map between the UV cutoff and what it means in the bulk?
Yeah, that's a very good question. So yeah, unfortunately, I don't know how to map this specific UV cutoff to what we have in the bulk. In the bulk, when we actually do computations in the bulk, we use a different cutoff in the bulk, just because I don't know how to map a lattice in the field theory to the bulk. And we sort of just guess that similar terms, just depending on the UV cutoff, will appear for any UV cutoff that we take. I mean, it's sort of a natural expectation that nothing here really strongly depends on the specific UV cutoff that I chose. So we expect that the same dependence on the UV cutoff will appear whatever we do on the ADS side, and we have checked that explicitly in the ADS theory that we get. But indeed, it's a bit unfortunate that the cutoff in which it's easy to derive this mapping on the field theory side is not a convenient cutoff for the ADS side. So in practice, indeed, we do use other cutoffs, and that's perhaps some loophole in the derivation that I'll derive that it would be nice to understand better. Indeed.
Oh, okay, great, thanks.
Okay, so in the second step, I'd like to now expand this bilocal field in representations of the Euclidean conformal group, because that will help us to translate it into the ADS side. So what are the representations of the Euclidean conformal group? I mean, we're just going to use the standard representations that we all know and love, the ones of primary operators in a conformal field theory. So these representations are labeled by the spin j of the local operator, by the dimension delta of the primary operator in the representation, and by the position y of the operator. So each representation is labeled by these three labels. Now, our original bilocal field comes from the product of two representations sitting at two different points, x1 and x2, where both of them have the dimension of just a free scalar field and spin 0. So all that we need to do is now to take this product of two representations of the conformal group and expand it in a full basis of representations of the conformal group, and this can be done. And in fact, it was more or less done already in the 70s. So it turns out that this product can be expanded in representations that involve all integer spins j and involve dimensions that sit in what's called the principal series, namely their dimensions of the form d over 2 plus I times some real number. So those turned out to be a basis for expanding this product of two representations. And indeed, in this basis, the eigenfunctions of the conformal group in this basis are nothing but the 3-point functions that we would have in a conformal theory. So if we would have some conformal theory with an operator of a dimension d minus 2 over 2 and spin 0, then the 3-point function of two of those operators times an operator with dimension delta and spin j. So those transform in the appropriate way to give us a basis, a basis of eigenfunctions under the conformal group. And the claim is that we can expand a general bilocal field in this basis in this way, namely just expand it as a sum over j, an integral over delta over the principal series, and an integral over y of the 3-point functions times some coefficients. So we can rigorously prove that any bilocal function can be expanded in this way. So again, one should think of this as an actual 3-point function. Of course, in our theory, we don't really have these operators. So this does not really denote a physical 3-point function in our theory. It's just a convenient way to denote the specific eigenfunction of the conformal group that transforms in the right way. So it transforms as under the conformal transformations of y as a local operator of this form, and similarly under the transformations of x1 and x2. And again, one can show that this is a complete basis, so that when it can expand any bilocal function in this basis, and one can also invert it, namely I can express the c delta j's as some function of the etas. So I mean, the main subtlety in showing this is, of course, showing that all these integrals, I mean, so this is sort of a formal expansion of this basis. One has to show that all these integrals actually converge and so on. So there are various subtleties that I'll skip over, but if you're interested, I'll describe it in gory detail in our paper. So this is the expansion that we have for the bilocal on the field theory side. So that's sort of the second step of just, if you want, we can make a change of variables from this eta x1, x2 to these coefficients c delta j of these eigenfunctions. Now, on the gravity side, it's much less clear what we should even start from, because a priori, we don't even know what would be the right variables on the anti-de Sitter side, since it's supposed to be quantum gravity theory where the space-time itself fluctuates. But what we'll do is we'll just make the simplest possible assumption about what we should have on the gravity side. Namely, we'll just assume that we're going to have spin j fields of all integer spins living just on a fixed ADS background. Now, at first sight, that sounds very strange to have in a quantum gravity theory where we expect the space-time to fluctuate. But we should remember that we're talking here about a high-spin gravity theory where we have a huge symmetry group generalizing the diffeomorphisms on the gravity side. And in fact, one can show in classical high-spin gravity that it is possible to rewrite any solution to the classical high-spin gravity equations of motion. One can always gauge fix the theory such that one can write its fields as living just on a fixed ADS background and then having fluctuations around that background. So at least when it comes to classical solutions, we can always describe those as living just on a fixed ADS space, where we have, again, fields of every spin living on that fixed ADS space, and that includes the spin 2 field that would describe the fluctuations of the metric on that space, but here we just write it as living on that fixed background space. So we imagine that we somehow did this gauge fixing also in this complicated quantum high spin gravity theory, and rewrote it as having fields that just live on some fixed ADS background. And of course, the justification for that will be that we'll show that we can map our field theory to this theory of fields just living on a fixed ADS background.
So Ofer,
Yes.
does this mean the causal structure is always in some sense trivial, like no black holes or whatever, or is it?
Well, causal structure is very complicated to discuss since this is highly non-local theory. I mean, so I don't know even how to discuss the causal structure here, unfortunately. So that's maybe one thing that helps. Of course, I mean, these high-spin gravities are so non-local that that you can even gauge fixed the metric to be whatever you want. So obviously that means that the causal structure is very strange in these theories. But I mean, well, it is what it is.
Okay, great. So there's no such thing as a
Right. I mean, so of course we do have the causal structure on the CFT, and I mean we're going to map it to the ADS side, so that will give us some induced causal structure if you want on the ADS side. But I mean, it's going to be it's going to be highly. I mean, the mapping is highly non-local, so there's no useful. I don't know any useful notion of causal structure in this case on the ADS side.
Okay, so in that sense, nothing funny happens when you go to high temperature or whatever that would correspond to putting in a black hole.
Well, that's okay. Maybe we can discuss that at the end. I mean, so it's well. I mean, if you want to discuss going to Euclidean finite temperature, then that's actually somewhat subtle. But I mean, at least if we discuss it in Lorentzian spaces, just going to some high energy states, then I certainly don't expect anything subtle to happen. But anyway, for now, I'm just assuming that we have these fields living on a fixed ADS space. I mean, I think what you're implying, Eva, is that probably, I mean, you would expect that when it's at finite temperature, you may have some phase transitions, say, between different topologies, and then this may be obstructed and so on. So that's definitely possible. So here, I must insist that I'm only working really on flat space and so on. So I don't want to have any circles or anything. And then the claim is that there's really just this single topology, and on that topology, I can always, well, what we're sort of showing by construction is that we can, in this case at least, map the theory just to fields living on this fixed metric on ADS space. So our field variables on the gravity side are going to be just these spin J fields living on ADS space. And once we assume that, of course, we know how to decompose these fields under the isometries of ADS space. If we just take general massless spin J fields and decompose them, we actually get more representations than we had in the previous step. But if we impose as extra conditions that we're going to look only at transverse fields, so for spin J equals bigger than or equal than 1, we're going to impose this transversality constraint, that's this equation. And we're also going to take these fields to be traceless. So it turns out that if you just look at massless spin J traceless transverse fields living on ADS space, just imposing these constraints, then what we'll find is that when we expand these fields in representations of SOD plus 1, we're going to find exactly the same representations that we had on the field theory side. So if we just take such a transverse traceless spin and expand it, then again, we have to expand it in eigenfunctions of the conformal group that transform as dimension delta spin J and are labeled by position Y. And in this case, these eigenfunctions are in fact nothing but the bulk to boundary propagators in ADS space from a point Y on the boundary to a point in the bulk with the appropriate mass and spin. So these bulk to boundary propagators transform in the right way to be the eigenfunctions of the conformal group in this case. And the claim is that, again, we can expand any spin J field living in an anti-de Sitter space in this basis of eigenfunctions, which is labeled in this case, well, for a fixed spin J, it's labeled by this dimension delta and by the position Y. And we have some coefficients C tilde of delta and J, which are the coefficients of this expansion. And again, the claim is that this is a complete basis. So we can always expand any spin J field in this way. And this expansion is invertible. So we can also write these coefficients as some linear functional acting on this spin J field. So that's the third step in the correspondence, just showing that if we had spin J fields living on ADS space, we could again translate them to these variables C delta of J, C tilde delta J. And then once we do that, then sort of the fourth step is almost obvious. We have exactly the same representations appearing on both sides, which means that we can construct an ADS CFT mapping just by identifying the coefficients C delta of J that appeared here in the expansion of the bilocal field that we started from. We can just identify them with these coefficients C tilde delta of J that appear in the expansion of the spin J fields in ADS space. And in this way, construct a mapping from the bilocal field to the fields in ADS space, which is consistent at least with the conformal symmetry. Now, in fact, there is some freedom in doing this. I mean, we can identify the C deltas in the ADS side with the C's up to some arbitrary constants F delta J. Now, it's not surprising that we have some freedom here because so far we haven't imposed any constraints on our theory on IDS space. So for instance, if we have some field theory, we can always do some redefinition of the fields as long as it's consistent with the isometries of ADS space. That would give us another theory that should also be consistent with our mapping. So we think of these arbitrary constants F delta J is corresponding to some linear field redefinitions that we can do to our bulk theory. And we can choose them just in any way that's convenient to us. That's just a choice of this field redefinition in our bulk theory. So anyway, given any choice for these F delta J's, we now have just an explicit mapping between our field theory variables, in this case, this bilocal variable that we started from this eta x1, x2. We can just map it explicitly by this formula. Again, the details are not so important, but these are just some explicitly known functions. So given eta, we can just plug it into this formula and obtain the fields phi j in the bulk. And similarly, this mapping is invertible. So given the spin j fields in the bulk, we can just have this explicit linear mapping that maps them to this to the bilocal operator that we started from. So all these terms here are just explicitly known operators, except for these f's that are these arbitrary coefficients. Now, a schematic way to understand why this mapping makes sense is that we can think of the center of mass. So on the field theory side, we have this field labeled by two positions in spacetime, x1 and x2. We can think of the center of mass position of these 2 points as corresponding to the position x here of the transverse variable or the variables along the boundary of the ADS space. We can think of the radial position in ADS space as coming from the absolute value of the distance between these 2 points, and then we can expand the rest of the distance between these 2 points in spherical harmonics, and we can think of the spin j field as coming from expanding this bilocal field and the spherical harmonics in the relative distance between these 2 points. So in terms of sort of just counting, that's why it makes sense to map these bilocal fields in a d-dimensional theory to these spin j fields living in ADS space. But in any case, I mean, this is just a completely explicit mapping between the two sides, which is, again, consistent with the conformal symmetry. I mean, so far, we haven't imposed any other constraints, but it is at least consistent with the conformal symmetry. And now, given this mapping, we can just plug it into the original action that we constructed back in step 1. And that gives us an action for these fields in ADS space explicitly. And again, also, of course, we can also just transform the measure of the path integral. This is just a linear change of variables. So this step, transforming the measure, is trivial. So again, as long as n is large enough, such that we could do the first step in the field theory side, this just gives us an explicit mapping between the field theory and this path integral on ADS space that gives us a path integral for this quantum high spin gravity theory on ADS space. Again, we can explicitly write down this action by just taking the action we started from and plugging in this space of variables. This action is completely non-local. I mean, this change of variables, as you can see, it's highly non-local. I mean, of course, we have an integral over these points x1 and x2, so it's completely non-local, but it is completely explicit. And again, by construction, since we constructed all steps in this mapping explicitly, this path integral over these fields in ADS space reproduces the conformal field theory order by order in 1 over n. Again, this change of variables makes sense as long as n is large enough, but order by order in 1 over n, you can just follow all these steps and show that this action that we get in ADS space reproduces for us the original field theory. Now we can choose, we can make now a choice of these arbitrary coefficients f to simplify our action, and it's convenient to choose them such that at least the quadratic term in the bulk is local. So we can choose these coefficients such that the quadratic term in the bulk is local. So for each spin j field, the quadratic term in the bulk turns out to take this form. Now, this part of this form is what we expect. I mean, so we would have expected to just have a massless spin j field sitting in ADS space. So if we just had the standard kinetic terms for these spin j fields, then those would just be the first Laplacian term here. I mean, this is just the mass corresponding to a operator of dimension d plus j minus 2 and spin j, which is what we expect for these massless spin j fields in the bulk. So if we look at the spectrum of this theory that we get in the bulk, we do find the expected massless spin j fields of all spin coming from this part. But we do also find some negative modes. I mean, unfortunately, we find this kinetic term that's quartic in derivative. So that also gives us some ghost modes that are massive. So in addition to the physical modes, we find here some massive ghost modes whose propagator is negative. We don't completely understand what's the role of these ghost modes. Presumably, they're related to this huge gauge fixing that we had to do. I mean, I remind you that we're the theory that we get on the ADS side now includes just these physical spin J fields living on a fixed ADS side, but the idea is that these fields came from some huge gauge fixing of a theory that we started from that had diffeomorphisms and this huge high spin symmetry beyond the diffeomorphisms, but here we gauge fixed it to get some completely, these fields phi j are well defined. I mean, we mapped them from the field theory, so these are some gauge invariant observables and some fixed gauge in this high spin gravity theory, and presumably this gauge fixing somehow led to the existence of these extra ghost modes. But again, their presence is necessary for our mapping to work, since again we just derived explicitly the equivalence between this ADS path integral and our original path integral. So these ghosts somehow have to be there for this mapping to work. But of course, the more important thing is that we do reproduce the expected spectrum of massless spin J particles in the bulk. Now the interaction terms are much more complicated than this. Yeah, sure. This is a good time for questions about this. Yes.
So you're saying that the field theory doesn't automatically give you just
right. So you would have expected that, but at least in this Euclidean mapping that we did, it does not automatically give us that, but it gives, of course, this is a completely optional mapping. I mean, again, we're mapping the full path integral, and the path integral that we find has this quartic term, such that if we would then in Lorentzian space at least try to use that to compute a spectrum of particles, we would naively find also ghost modes in addition to the expected physical particles. Of course, since we're doing an explicit mapping, we expect that these ghosts should completely decouple and so on. But we're just doing the Euclidean mapping. I mean, it's one of the open questions at the end will be indeed to show in Lorentzian space that those things indeed decouple. But for now, I'm just discussing the Euclidean path integral, and in the Euclidean path integral, we do have this quartic term. I mean, it is what we get, and it is necessary to reproduce the field theory.
Okay, I mean, in the field theory language, everything is consistent, right? Like with variance.
Well, again, it's Euclidean theory, but I mean, whatever consistency means is an Euclidean theory. I mean, it is whatever. So it satisfies all the, of course, it's a free theory. It obviously satisfies all the consistency conditions of a free Euclidean theory. And so whatever we get on the gravity side, had better also make sense, at least as Euclidean theory. And then we hope that it's also possible to continue this to Lorentzian space, and then these ghosts should somehow decouple, but that's stuff we haven't done yet. So for now, I'm just presenting the Euclidean mapping.
Could I just ask, it seems like you used that that there was only the principal series that was.
Yes, indeed. So the principal series it turns out that it is a complete basis for this specific product of representations.
Why is there no discrete series?
Well, it just doesn't appear in this product. I mean, when you take this product, one way to think about it, which is actually the way that we derive this, I mean, so you could start by taking a product of two representations in the principal series. So that was analyzed indeed a long time ago by Dorber and collaborators. And in that case, you do just find that only the principal series appears in the product of those representations. And then you can analytically continue that product to delta that is off the principal series. And you find that you can still expand the product even when your original operators are away from the principal series, you can still expand them just in the principal series. I mean, so that is a complete basis. So I agree that you may have thought that you need all the representations, but you just don't need them. I mean, this turns out to be a complete basis. So I agree, it's a surprising fact, but it's just a true fact about representations, at least of the Euclidean conformal group. And again, we can just explicitly invert this. I mean, so it's explicitly a complete basis.
Yeah, but one could imagine that there was some ambiguity in the inversion, and that would in fact be some gauge modes, or otherwise that you could expand on some discrete series or whatever. I don't know. Right,
indeed. But that doesn't happen. I mean, there is some subtlety actually when doing it. I mean, you do have, if d is less than 4, you do have to slightly deform this contour for the scalar fields. And so you do have to capture some extra pole that's to the left of the principal series in that case. I mean, so it's not completely straightforward, but say for spin bigger than 1 and for d bigger than 4, even for spin 0, then it is completely straightforward. And you do have just the principal series. If for the scalar case, when d is less than 4, you do have one extra contribution from the discrete series with delta equals d minus 2.
So there's that slight subtlety, but this whole thing works when d is equal to 2. I mean, so when this whole thing is just SLN.
Well, this whole thing, I was always assuming that d is bigger than 2. D equals to 2 is much more subtle because there, if you remember, I mean, even the 2-point function would be logarithmic and d equals to 2. Yeah. So the whole thing does not make sense for d equals to 2. So I'm always assuming d bigger than 2. It would be nice to do this also for d equals 2, but I don't know how to do that. So this whole story only makes sense for d bigger than 2. Okay, so this is the quadratic term that we find for this mapping, and then the other interaction terms, I mean, they're explicit, but they're very complicated. For instance, this is the explicit form of the interaction between three fields. So you can see we have these three spin J fields in ADS space. Their positions are integrated over, and then we have also various additional auxiliary integrals. All these functions are completely explicitly known and so on, but they're just complicated. So we have this complicated non-local interaction between these three fields at different points, and it is suppressed by 1 over square root n, as we would expect. It's not very illuminating, but I mean, you can just at least compute, say, the leading one loop correction to things using this non-local action. But of course, I mean, sort of by construction, it just maps to the same computation in the bilocal field. I mean, so it does reproduce for us the correct action on the field theory side. And we believe that this action that we get is just a gauge fixed version of some action for the high spin gravity theory on ADS space. And in particular, we believe that the classical equations of motion that we would find from this non-local action should agree with the known Vasiliev equations of motion in some gauge. However, we don't know exactly which gauge fixing you have to do to get this, so we didn't show this, but at least if you assume that high spin gravity is unique, then presumably you should get the same equations of motion also from Vasiliev's theory in some gauge. But of course, this mapping goes way beyond just the classical equations of motion. I mean, first of all, it is a completely off-shell mapping, and of course, it also makes sense at the quantum level in the sense that you can compute loop corrections with this action, and as you can explicitly show they do make sense and they do reproduce. I mean, of course, with the appropriate counterterms and so on that we carried over from the field theory, and they do reproduce the original CFT computations. I mean, our mapping, it's not even, a priori, it's not even obvious that our mapping is consistent with the usual on-shell mapping for the local CFT operators. So we know that those map to the expansion of the bulk fields near the boundary. I mean, that's not completely straightforward to show using our mapping, but you can show that if you take these bilocal fields and you expand them near the, these fields in ADS, you expand them near the boundary, then they do reproduce the local operators as you would expect. Now, the fact that we have an off-shell mapping means that we're not just limited to studying this free field theory, but we can also study any deformations of this theory that we want. So one thing we can do is we can add a mass term, and then we can obtain an ADS-CFT dual to the massive free scalar theory, which is, but we can also study interacting theories. So one easy thing we can do is just add a phi to the fourth interaction and flow to the critical UN vector model, which is just a generalization of the Wilson-Fisher fixed point. So this is just a double trace deformation in this language, and we can easily add it to the field theory side, just follow the mapping and describe that also on the gravity side. Similarly, we can describe a version of scalar QED by just coupling a U1 gauge field to the spin 1 current that we have in our theory, and that gives us the UN invariant sector of scalar QED, so QED coupled to n scalar fields. Now, in both cases, you can view the deformation as sort of being the analog of a double trace deformation. So as expected in general, in ADS-CFT, whenever we have a double trace deformations, we find exactly the same bulk theory in these cases, but just with different boundary conditions. But here, again, we don't need to assume that. That's just what we explicitly get. I mean, we just add these fields on the field theory side, follow the translation to the gravity side, and we find that we do get, indeed, as expected, exactly the same bulk theory, but now with different boundary conditions. I mean, so in the scalar QED case, we just find a different boundary condition for the U1 gauge field and the bulk, and otherwise exactly the same non-local interactions. In these cases, either in the UN critical model or in the scalar QED case, the 1 over n expansion is now non-trivial. I mean, of course, we do get 1 over n corrections in these theories, but by construction, it is still reproduced by our bulk action. So let me summarize. In this talk, I presented explicitly a construction of a quantum gravity theory on anti-de Sitter space by just taking a quantum field theory and mapping it to new variables that look like a quantum gravity theory on ADS space. The result is highly non-local, as expected for this specific example of the ADS-CFT correspondence, but by construction, it agrees with the quantum field theory to all orders in 1 over n. So there is a sensible expansion in loops in the bulk, and to all orders in 1 over n. By construction, it reproduces the original field theory that we started from. So one can view this as a derivation of the ADS-CFT correspondence for this case. And as a side effect, it also gives us a quantum definition of what we mean by a high-spin gravity theory, at least in some specific gauge fixed version of this high-spin gravity theory. Now, for finite n, which means once we include non-perturbative effects on the gravity side, we find that in principle, we can still map to the same variables, but our bilocal variables, and therefore also the gravity fields that we obtain, now obtain highly complicated nonlinear and non-local constraints. So some nth powers of its gravity fields are now related to nth powers of completely different gravity fields at different positions. So the gravity description does not seem useful once we try to describe finite n effects. So the bottom line, at least in this example, seems to be that gravity is very good as an effective semi-classical description that captures the large unlimit on the field theory side, but it's just not a good variable to use if we want to discuss the full quantum theory. And in particular, quantum gravity in these large numbers of dimensions cannot just be viewed as a path integral over metrics, but rather in the full quantum theory, I mean, the metric obeys highly complicated constraints, and it's just not a useful variable. So there are many future directions and open questions. As I already said, it would be nice to show explicitly that indeed the action that we obtain gives rise to the same classical equations of motion that we would get from Vasilyev's theory in some specific gauge choice. It would be nice to somehow ungauge fix our theory so that we would be able to write it in some formalism where we explicitly see this high spin symmetry and also the diffeomorphisms. Again, our theory just lives on a fixed ADS space, but it would be nice, of course, to show that, and it has the massless spin 2 modes that we know should make it into a consistent theory of gravity, but it would be nice to explicitly show that putting these two together gives us a diffeomorphism invariant theory. It would be nice to also relate our derivation to other derivations that were previously done in somewhat different languages. There are many possible generalizations, some of which we're working on. It would be nice to generalize this to the mapping of free fermions to high-spin gravity theories. It would be nice to consider other manifolds. And as I mentioned, the d equals 2 case is somewhat subtle because of the logs in this case, but d equals 1 should be easy, and that's another interesting generalization. It would be very nice to understand better the finite n constraints that we get, what they look like on the gravity side. Again, on the field theory side, they just tell us that the rank of this bilocal matrix G has to be less than or equal to n, but it would be nice to understand what they mean on the gravity side. Somewhat surprisingly, these constraints tell us that even empty ADS space is just not an allowed configuration for finite n, because you find that empty ADS space, which in this language is eta equals 0, that does not obey this constraint that the rank of G should be less than or equal to n. So somehow these constraints are so constraining that even empty ADS space does not make sense. As we already briefly discussed, it would be very nice to generalize this to the Lorentzian case. So then we have to use representations of the Lorentzian conformal group, and that's work in progress. The nice things to understand there would be, of course, to show that these ghosts that we seem to get, we need to show that they decouple and that we reproduce the correct Hilbert space. And then we can also try to analyze black holes. Of course, in this free theory, black holes would not really thermalize, so I'm not sure if they should be called black holes, but still, it should be possible to construct generic high energy states on the field theory side and see what they map to on the gravity side. One could also try to play similar games for the Cf2 correspondence. So as is well known, there is a generalization of the specific example of Cf2 also for the Cf2 correspondence, and one could try to construct a similar mapping to the bulk there. Of course, I have no idea what the interpretation would be in that case of this path integral that we get in the bulk, but it could be a nice game to play. Of course, the much harder problem is to generalize all this to matrix theory, where we have also gauge fields. In that case, we do expect that we would probably need different bulk topologies, and of course, interacting gauge theories should be even more complicated. So unfortunately, I don't have anything to say about that. And the main interesting question is, what lessons can we draw from this very simple example for more realistic quantum gravity theories, where we do expect to have fluctuating space-time, and we want to have flat space-time or positive cosmological constant, or at least an approximately local theory, even in ADS space. So it's not clear which lessons we can draw, and that's the question that I want to end with. So thank you all for listening.
Thanks a lot, Ofer, for the very nice talk. You can unmute and thank the speaker. Yeah, questions for Ofer?
I had a question. Is there a way of gapping out these higher spin fields in the bulk, and what would that correspond to in the boundary?
Yeah, that's an interesting question. It's well, one of them is, you mean also the graviton or just the higher spin modes?
Yeah, just the higher spin modes. Like
yeah, well, the higher spin modes, in some sense, whenever we include interactions, they do obtain a mass at order 1/n. I mean, so of course, these say when we go to the critical theory, then of course the higher spin currents are no longer conserved at order 1/n. So these high spin fields do always get a mass from loops. I mean, so say if you compute their propagator in the bulk, you would see at order 1/n that they do become massive. So in that sense, they are gapped by.
Oh, I see. You're saying the interactions sort of cause that already.
Right. And if we don't discuss the free theory, but say this critical UN model, so in that sense, I know how to gap them. but I mean, it would be nice to gap them already classically. Of course, I mean, of course, if we want to go to an approximately local theory, we'd like to be able to gap them classically. But yeah, that unfortunately I don't. Yeah, that I don't know how to do, unfortunately.
I see.
So yeah, so that's presumably part of this generalization to matrix theories. Of course, in that case, it should be possible to do that. But yeah, I don't have anything smart to say about that, I'm afraid.
I see. Thank you.
Yeah, I have a question, Ofer.
Yes, please.
If I have two copies of the theory, and I entangle them in something like the thermal field double state, is there any indication of a geometry associated with that?
Yeah, that's a very interesting question. We're actually trying to think a bit about that. I mean, following the paper by from your Stanford group and so on about doing that for the SYK case. But yeah, I'm not sure. I mean, so it's not obvious how to try to repeat the same steps that were done in the 0-dimensional or 0+1 dimensional cases. We haven't been able to see how that would.
Well, I'm not sure what you mean. I just meant, is there any
in this
indication
case?
of a
you could try to say if you have two copies, you could try to go to say yeah, well, I mean, one thing you could try to do is to try to go to say bilocal variables between these copies and see that you can form wormholes or something like that. So yeah, I'm not sure if that's where you were going, but one thing you could try to do is that. But yeah, but I don't know how to show that. I mean, certainly. So yeah, I mean, in our mapping, it doesn't naturally come out, and yeah, that's a very interesting question.
I think a related question. I think it's a related question. Is there any interesting? Does this gravity construction give any insight into entanglement in the boundary theory? To put it simply, is there a kind of RT?
Yeah, I'm not sure if I'm not even sure how to discuss that in the bulk when it's so non-local in the bulk. Yeah, I don't know how this gravity comes from entanglement picture should work when gravity is so non-local. I mean, I don't really have a good intuition for that. I mean, yeah, it's in this example, indeed, it may be interesting to study that to see what becomes of that relation when gravity is so non-local. But yeah, I mean, of course, I mean, you could also ask that in standard Idscft at weak coupling on the field theory side. I mean, when gravity is also highly non-local, I mean, what becomes of entanglement in that case? And yeah, that's a very interesting question, and I really don't know. I mean. I mean, I can't even imagine what the RT surface would look like in such a non-local theory.
Yeah, right. Okay, thank you.
Hey, Ofer, thanks for the nice talk. Your construction, you're leaning extremely heavily on the symmetries that in flat space-time, you have the full SO D+1,1. So are there any ideas as to how you might, so if you want to talk about Euclidean black holes, for example, you might want to put it on RD-1 times a circle, then you've broken the symmetries, so it's not obvious that the same construction works. Are there any ideas how you might put it on different backgrounds?
Yeah, so, well, there are two different parts of that question. I mean, I think, it's true that we use SO D-1 heavily, but I expect that if we put it on different manifolds, that say are topologically the same as the sphere, I'm not sure if it would be so difficult to go through with it. I mean, I'm not sure if, I mean, yeah, it would be more complicated, but not that difficult. But putting it on a circle, that is much more difficult, because then you have to say how you impose this projection onto singlets of UN. So if you really want to discuss the theory, say on a thermal circle, then you have to impose this projection. And as you well know, I mean, to do that, you have to really impose some UN gauge fields and integrate over a UN holonomy of that circle. So then it becomes sort of as complicated as a matrix theory. So even just this free theory, once we really want to impose the UN projection consistently for the theory on a circle, it becomes very complicated. So that would be the main complication with putting it on a circle. So if I put it on circles which are topological, I mean, they don't have any pi1 or whatever, then I think a similar mapping should work. But once you have a circle, then this would, I think, really only make sense if we would introduce also UN holonomies of that circle. And that I don't know how to do. I mean, of course, there are similar problems in SYK, I mean, conceptually of also needing to understand there how the projection to Owen invariant work. And I never understood it in that case. I don't know, maybe you guys understand it better. But in this case, it would certainly be necessary for this whole correspondence to make sense that we do somehow project onto the UN singlet. So we would have to introduce these holonomies, and then I don't know how to do this mapping. So that's another interesting open question.
Let me ask a question. I mean, as you know very well, I mean, it's a very interesting question how these these finite end constraints are implemented in the bulk.
Right.
And you know lots of examples, people on this call. I mean, the implementation of the giant graviton kind of constraints by D-branes.
Right.
Or you can imagine representing delta functions of these G's as by some integral of an auxiliary field that's wildly fluctuating.
Right.
The sigma field is a good candidate. And so it's not, I mean, in some sense, that's even things like these wormhole configurations are, representing the finite dimension of Hilbert space kinds of phenomena. So it seems that finding novel ways of implementing these constraints is a really interesting goal.
Right.
And that, we know a little bit about how that works in SYK, but not enough. And so you might imagine that you might be able to see maybe some of the non-perturbative phenomena that you know very well in these models, maybe even the baryon operators are the way in which this constraint is implemented. That the existence of that operator is the signal that all these bilocals are not independent.
So I think here, I'm not sure if that's the right intuition, because here these constraints are really highly non-local. I mean, so it's not like, say, for the giant gravitons, where just locally you turn on, you take products of these operators and so on, and eventually just locally it becomes some different state. I mean, here are these constraints. I mean, say if you look at the case of n = 1, I mean, these are really just constraints at any arbitrary points in space. I mean, this is in the field theory space, but also when you map it to gravity, it would become, of course, then this maps to some integrated constraints over the graviton field all over space. And these constraints here are really much more horrible than those constraints. So I don't think the giant graviton intuition is good. I mean, the intuition of putting in auxiliary fields and so on, that I think is probably a much more useful way to think about it. And indeed, I mean, that's exactly what I meant when asking for solving these finite end constraints. So hopefully there is some way to do it in a useful way with auxiliary fields. I mean, again, probably, and I agree that it's completely analogous to the questions in SYK, and in both cases, hopefully one can find useful ways to do that, and eventually even understand the finite end theory. But I think I don't have any good ideas for how to do that, but hopefully more progress can be made on that. Yes, but I don't think it will be like giant gravitons or even baryons. I mean, I think it's more complicated than that, but hopefully it can.
I mean, we had a sense that in this work paper with Shai that, if you will, the finite temperature transition is basically driven by that independence, as you know, by that dependence. That's sort of when you have more bilocals than you should present. And
well, you guys were looking at the local operators. I mean, so say for the local operators, that's how that works, of course. But here, because the variables in Urbach are related to these bilocal operators, then
no, I meant we meant the bilocal operators. We showed that the set of all bilocals with this paper with Shai on the vector-like models.
Right. So I thought there is just analyzed the thermal partition function on S2, and the Hilbert space there just maps to the local operators. I mean, it's not. I'm not sure in what sense it's bilocal operators.
Well, I mean, if you count the spectrum of bilocal operators, that was going to, it reproduced that at low temperatures, and it was that the entropy of the bilocal operators got too big compared to the entropy of the local field theory.
Well, but there it's not really the bilocal operators. So there it's really the products, just the products of the local operators. I mean, there you have the low temperatures, just the scads of the local operators. I mean, again, because you're describing the field theory on a sphere, which is the same as studying the space of local operators. So there's just taking products of local operators, and again, and those eventually transition as you described. But I'm not sure if that's the right intuition here for the field theory in this flat space where you really, it seems like you need to describe the bilocals. I mean, maybe it is. I mean, I don't know, but it seems somewhat different to me.
Okay, I'll have to think about it. I thought that was what was going on. And then the question I was going to ask, I'll just throw it out. Maybe it's what you just said is the resolution of that you might want to look for a precursor of that thermal transition. And we weren't sure that the precursor wasn't related to some of these baryon operators. There was a problem with the scaling, but that whatever that thing might be is would be the would be the first indication that this lack of independence. So it might be that you're right. That the sphere
but that would be the analog of the giant graviton story and so on. So that would be sort of the,
I guess it would be a little bit like that.
Right. And I'm not sure if that's really the type of thing that's needed for the variables that we're working in.
All right, I'll go think about that. I maybe I've missed the point. Okay, I just wanted to raise those issues. Okay, but it sounds like you.
Yeah, but certainly, I mean, if of course we could also discuss our theory on a sphere times time and so on, and then in that context, indeed, if we discuss the Lorentzian version of that, then indeed what you say would be very relevant and so on, and in that context we would expect a transition of that type. I mean, so there in the Hilbert space certainly that would just map to the local operators, and we would have a transition like that. But the mapping in that case may be somewhat different. I mean, so again, we haven't analyzed the mapping for the theory on a spatial sphere times time and so on. I mean, that's.
Yeah, I mean, let me ask you another question though about the extent of the non-locality. I mean, there's a question of sub-ADS locality and super ADS locality.
Right.
I thought these higher spin theories were local on the bigger than ADS scales.
Right.
So and so things like tensor networks give like reliable RT surfaces where you ignore the sub-ADS locality, and you have tensors that represent like an ADS region.
Right.
And I might have thought, so given like that you get the nice log in the conformal field theory on the boundary, 1+1 dimensions, where maybe let's say you do your math in 1+1 boundary dimensions.
Well, there's different. I mean, so we haven't done it explicitly. So yeah, I'm not sure if we can get that log. But certainly we reproduce the field theory. So we do reproduce everything in the field theory. So yeah, so that's a very good question. I mean, so I sort of glossed over that point that indeed in our formalism, it's not obvious that the theory is local at scales bigger than ADS. I mean, but you can just look at these interactions, and I think at least in some cases we were able to see that they do die off at distances that are bigger than ADS radius, but it's not. I mean, but we haven't shown it in general. I mean, so I don't know. I mean, we expect that it should be local at scales that are beyond ADS scale, but we haven't shown that.
I mean, you expect that because the masses. I mean, the fields. There's some massive. The fields get massive beyond ADS.
They are massless fields. I mean, they're as massless as a spin J field can be. I mean, I think this expectation is mostly based on the fact that in the Vasiliev theory, and of course that may be in a different gauge for the Vasiliev theory, but in some gauges where you write that, you do see that the higher derivative terms are suppressed by parts of the ADS scale. So that does seem to be the non-locality scale.
Yeah, so I guess that's what I meant. Sorry, that's that the higher derivative terms were suppressed by an ADS scale.
Right. So that's far from evident in our formalism. We hope that that's true, but again, these are horrible functions. I mean, so we think that these functions indeed do decay fast enough at distances that are bigger than ADS scale, such that the theory does become approximately local at these scales, but we haven't shown that explicitly.
Okay, well, let's be optimistic. Since after your talk, let's say that's the case.
Yes. Okay.
Then you might think you can derive RT type formulas, for distances much larger than ADS.
Yeah, that's right.
That might be the hope.
That. Okay. Yeah. Good. Okay.
You'd have some, something as good as a tensor network derivation.
Yeah. Good. Okay. Yeah. Good. So so that's a better answer to Lenny's question. Yes, definitely. That you may hope that at least in these distances much bigger than ADS, you may hope to do something like that, and it would be very interesting to try to do that. Yes.
Okay. All right. So thanks. I appreciate your.
But I'm not promising that it will. I'm not promising that it will succeed because again, we haven't shown that it's really even approximately local at these large scales. But yeah, probably. Okay. I mean, if you can show this entanglement computation, of course, that would show that.
Presumably. I guess this talk is being recorded, so you need to be cautious. So, all right, your caution is noted.
Yes.
Okay. Are there any other questions? Okay, if not, let's thank Ofer once again for the very nice talk.
Okay, thanks. It was good to see you all, and hopefully in person.